Okay, the first 8 weeks of pre-calculus has been just a more in-depth view of algebra than we did in college algebra. We certainly did a lot of new things in the last 8 weeks. The last 8 weeks of pre-calculus are trigonometry, and in calculus, the trigonometric functions come into play very early. That's why our calculus book is named Early Transcendental Functions. You have to know your trig from day one in there. So this 8 weeks is getting you ready for just that chapter 1 of calculus. Let's talk about angles. I asked you to read pages 334 and 335 before class today, and so you should be familiar with all of this notation, everything that's listed in boldface type in the book on those pages. You should be familiar with that already, but I'm just going to run through it with you. We're talking about angles, and in geometry, we defined angle as a set of two rays joined at some point. Here's some point, call it point O. If we extended two rays from that point, and we call those two rays or half lines line 1 and line 2, then if A is some point on line 1 and B is some point on line 2, then we've just created the angle AOB, and that's the notation for angle AOB. Now, in trigonometry rather than geometry, we're not going to talk about an angle as being two rays joined at some point. We're going to talk about an angle being a single line. I'm going to use this for my angle. A single line that's rotated through the Cartesian coordinate system. Now, wherever that line begins, that's called the initial side. So this would be my line 1. And when I rotate it through the Cartesian coordinate system, wherever it stops is line 2. And so I've created an angle. If this is my Cartesian coordinate system, I've created an angle. Play like that meets somewhere at the origin, but I've created an angle by rotating the initial side to some point where I end up on the terminal side. This is still called the vertex of the angle. If we start with some initial side and we rotate it either counterclockwise or clockwise until we end up in the same place, end up back where we started, then the initial angle and that angle are called coterminal angles. Coterminal angles have the same initial side and same terminal sides. A straight angle is an angle whose sides lie on the same straight line. So you can think of this as being a straight angle. Its two ends point in opposite directions. Nothing after that. If we move these angles to the rectangular coordinate system, then we can talk about angles that are in standard position. Standard position of an angle is just an angle with its initial side on the positive x-axis and its origin or its beginning at the origin. If we move that angle, if we rotate that angle clockwise, that's called the negative direction of an angle that's in standard position. And if we start in standard position and move that angle by rotating the initial side counterclockwise, that's the positive direction. Now, the reason that that's the positive direction, it's kind of counterintuitive now that we have clocks that go in the other direction, but initially, before clocks were invented, um, it makes sense to call the positive direction the way that you're going through the quadrants. If you're going in a counterclockwise direction, you go through quadrant 1 first, and then quadrant 2, and then quadrant 3, and then finally quadrant 4. So the counterclockwise rotation gives you a positive angle, a clockwise direction gives you a negative angle. And you will see a lot of Greek letters in trigonometry, because in trigonometry we use angles. We use Greek letters to represent angles. You need to be familiar with these symbols here. This is the alpha symbol. This is beta. This is gamma. And this is theta. And this is phi. That's pretty much the only angles we will use. Probably alpha, beta, and theta more than any of the others. To show you an illustration from the book, figure 3 shows 3 different angles that are in standard position. Figure 3 part A, the initial side started on the positive x-axis and then was rotated counterclockwise, so that's a positive angle with its terminal side in the 3rd quadrant. And the second illustration, again, its initial side is on the positive x-axis and it's rotated counterclockwise, so it's a positive angle, but this symbol indicates that it's rotated counterclockwise one entire time through the Cartesian coordinate system, and then a little bit more. Maybe since you know degrees already, I'll say that that looks like that line 2 ended up about 45 degrees from line 1, but it was rotated initially through the entire Cartesian coordinate system and then about another 45 degrees. And the third illustration here is a negative angle. It starts with its initial side on the positive x-axis and rotates a little over 2 quadrants to end up with its terminal side in the 2nd quadrant. Again, that's a negative angle because the initial side was rotated clockwise. Now, one way of measuring angles that you're already familiar with is degrees, and you already know that there are 360 degrees in a circle. So if we start with an angle in standard position and we rotate it either clockwise or counterclockwise, we will say that that is a 360 degree angle. A degree is 1/360th of a circle. If one entire circle is 360 degrees, then a 1 degree angle would be 1/360th of the entire circumference of the circle. Oops, I said 1/360 and I wrote 1/36. 1 degree is 1/360th of the circumference of the circle. At the bottom of this page in the book, we see some different size angles, and all of them start in standard position. This first one, the initial side's on the positive x-axis, and it is rotated 1/4 of the way through the circle, so that's a 90 degree angle. The second illustration, again, starts in standard position, but it rotates counterclockwise one time around the circle and then another halfway around the circle. One time around the circle would be 360 degrees, another halfway around would be 180 degrees, and so that's a 540 degree angle. The third illustration starts in standard position, but the initial side is rotated clockwise all the way through one quadrant and maybe halfway through another. So that's a negative 135-degree angle. And then the fourth illustration starts in standard position and is rotated beyond 90 degrees, but not yet to 180 degrees. That's a 150-degree angle. All right. If coterminal angles are angles that have the same initial and terminal sides, then we can find coterminal angles for any angle that we're given. Actually, that's the first couple problems you have in the notes. Oop, wrong notes, that's 5.2. Looking for 5.1. Ah, there they are. I didn't realize I had the wrong notes when this video started. Sorry about that. It was pages 324 to 326 that I asked you to read before break. And you need to understand the terminology that's in these first two examples. Example 1 says finding coterminal angles, angles that have the same initial side and terminal side. If we want to find two coterminal angles for a 570-degree angle, we could draw a 570-degree angle. 570 degrees would be, well, it's a positive angle, so I'm going to go counterclockwise. One whole time around the circle would be 360 degrees, and then another 90 would be 450, another 90 would be 540, and then another 30, maybe right there, would be a 570-degree angle. Now, let me think about that. 360 and 180 is 540, and then another 30 degrees would be a 570-degree angle. So if we wanted to find a positive coterminal angle, we could just go all the way around the circle again. We could add another 360. And if we wanted to find two positive coterminal angles, we could add another 360. Or, because this angle is more than once around the circle already, to get a positive coterminal angle, we could say before we got here and went another 360, if we just subtract 360, that gives us 210 degrees is coterminal with 570 degrees. Now, the only reason we subtracted there was this was more than 360 degrees to start with, so we could subtract 360 and still end up with a positive angle. To get the second positive angle, we couldn't subtract another 360, or we would have a negative coterminal angle. We could go ahead and get our first negative coterminal angle. If we start with that 210 and subtract 360, then our first negative coterminal angle is negative 150 degrees. If we wanted another positive coterminal angle, we could take the 210 and add 360 degrees. We would see that, well, that doesn't make sense because 570 degrees is the angle we started with. If we want another coterminal angle, we need to add 360 to the angle we started with. That would give us 930 degrees, I believe. Now, answers could vary on this. Some of you may have added 360 to begin with and got the 930, and then added another 360 from there and got 1,290. That would be an acceptable answer also. And then finally, our other coterminal, negative coterminal angle would be, we could start with the negative 150 and subtract 360, and we would have our second negative coterminal angle is negative 510 degrees. All right, so to get positive coterminal angles, just add multiples of 360. To get negative coterminal angles, subtract multiples of 360. Now we're going to skip this B part for a second because that's not in degrees. That's another way to measure angles, and we'll talk about it in just a minute. Some other terminology that you should be familiar with. A right angle is half of a straight angle and has a measure of 90 degrees. And then other special types of angles are acute angles, which are between 0 and 90 degrees, obtuse angles, which are between 90 and 180 degrees. Complementary angles have a sum of 90 degrees, and supplementary angles have a sum of 180 degrees. So you should be totally okay with that from geometry. If you want to find an angle that is supplementary to another angle, for example, if you wanted to find an angle that's supplementary to 30 degrees, you just subtract 30 degrees from 180. 150 degrees would be supplemental to 30 degrees. All right, what we said that a degree is 1/360th of the circumference of a circle. But what if we needed more precision than that? What if we needed something even more precise than 1 degree? What if an angle was smaller than 1 degree and you still wanted to give its measurement? Well, we break degrees down into more precise units called minutes and seconds. The minutes are denoted by just a single tick mark, and seconds are denoted by 2 tick marks. 1 degree is 60 seconds, and 1 minute is, no, I said that wrong. 1 degree is 60 minutes, and 1 minute is 60 seconds. So if you see this notation, you read it 73 degrees, 56 minutes, and 18 seconds. The next problems in the notes ask me to find an angle that is supplementary to theta. Well, that would be pretty easy if theta was given to me as just a whole degree, as for example 150 degrees. You could real quickly in your head figure out that 30 degrees is supplementary to 150. But if you need what is supplementary to an 87 degree, 13 minute, 52 second angle, you're still going to have to subtract that from 180. But if I just tried to subtract 180 minus 87 degrees, 13 minutes, 52 seconds, I wouldn't have anything to subtract the minutes and the seconds from. So just like we subtract in elementary school, when we're subtracting, sometimes we need to borrow. I can borrow one of those minutes and call it 60 seconds. I'm sorry, I said that wrong. We can borrow one of those degrees and call it 60 minutes. And then we can borrow one of those minutes and call it 59. I'm sorry, call it 50. Borrow one of the minutes and call it 60 seconds. What I was trying to write out to the side wasn't making much sense there. Borrow one of the 180 degrees, that'll get us down to 179 degrees. Then the degree that you borrowed, call it 60 minutes, but you have to borrow one of those minutes, so we're down to 59 minutes. and 60 seconds. If you took this 60 seconds and said it was a minute, added a minute back to the 59 minutes and called it a degree, we would be back to 180 degrees. So when we write that when we write that degree that we borrowed as 59 minutes and 60 seconds, then we can subtract. 179 minus 87 is, I'm double checking myself. That's 179, 46 minutes and 8 seconds. So a 92 degree, 46 minute, 8 second angle is supplementary to an 87 degrees, 13 minute, 52 seconds angle. An easier way to be more precise with the measurement of an angle, instead of using degrees, minutes, and seconds, it's easier just to use decimal degrees. 97.9 degrees is almost 98 degrees. We could change that to degrees, minutes, and seconds, but it would still be an angle that's almost 98 degrees. So if we wanted to subtract, or if we wanted to find an angle supplementary to that, and it's given to us in decimal degrees, all we have to do is subtract that from 180 as a decimal. Let me double check that. That's 170, 179, 180. An 82.1 degree angle is supplemental to a 97.9 degree angle. All right, it is time for something big. And let me just tell you that in the mail in the next few days, if you're in my class that's supposed to be live but has been moved online due to the coronavirus, in the mail you'll be getting all the notes for test 3, and you'll be getting a copy of a circle in the Cartesian coordinate system, and you'll be getting a little baggie with some triangles and some pointers in it. And I'm going to make a different video to show you how to translate this image into this image using the triangles and pointers that I'm going to send to you. But we're not quite ready for that yet. I want to talk about another way to measure angles, and other than using degrees or degrees, minutes, seconds, this other way of measuring angles is called using radians. And it's a little bit tricky to wrap your head around exactly what a radian is. So there's one thing I should have grabbed before I sat down. Let me just get something that will bend easily. Maybe a rubber band. In my live class, I would have provided you with a Twizzler, because Twizzlers bend very easily. But what I'm looking for is something bendable that is exactly the same length as the radius of that circle. So I'm just going to break that rubber band, and now I have a length of rubber band that is exactly the length of the radius. It's length R. To explain what a radian is, let me take this radius and mark it off, lay it around the circumference of a circle, and see how many times it goes. I'm going to put a little mark every time I get to the end of that rubber band laid off on the circumference of the circle. So that arc is the same length as one radius of the circle. That's the definition of what a radian is. Let me go back to the book for just a second and show you some other important notation. A central angle is an angle whose vertex is at the center of the circle. So if we have an angle in standard position and its center is at the center of the circle, then that's called a central angle. This is a central angle. The definition of a radian, back up to some other words, we say that the arc AP, if this is some point A and this is some point P, then the arc AP subtends some angle theta. So that arc AP subtends the angle, or we could say the angle is subtended by the arc. And now we have all we need to define a radian. A radian is the measure of this central angle subtended by an arc that is equal in length to the radius of the circle. This angle that I label theta, we would say theta is, it looks like in degrees it's maybe 60 degrees-ish, but to be more precise, that angle theta is 1 radian in measure if it is subtended by an arc that is equal in length to the radius. Now we know there are 360 degrees in a circle. How many radians are in a circle if we want a different way to measure the size of an angle? Well, let's just see how many times this radius will fit around the circle. This was the arc that subtended an angle of radian measure 1. But if we laid off another radius on this circle, trying to be a little bit precise here, then starting in standard position and going all the way here gives us an angle of measure 2 radians. If we laid the radian on the circumference of the circle again, the radius, not the radian, then here's the third time my radius fit around the circle. So if I started in standard position and went all the way almost to 180 degrees, that would be an angle of measurement 3 radians. One more time, and I have an angle of measurement 4 radians. Once again, I have an angle of measurement 5 radians. Once again, almost all the way around the circle, and I have an angle with radian, a measure of 6 radians, and I'm trying to figure out how much, obviously that's not another whole radian. Let's see about what fraction of a radian is. If I fold my rubber band in half, that's too big. It's not a half a radius long. If I fold that rubber band in half again, it just about covers that little piece that I have left. So I'm going to say that that radius goes around the circle 6 whole times, and because I folded it in half twice, I'm going to say about another quarter of a time. I'm going to say that 360 degrees, if we're measuring an angle in degrees, is about 6¼ radians. But let's write that as a decimal. 6¼ is about 6.25 radians. And then what if I told you that instead of 6.25 radians, it was closer to 6.2 radians, or 6.28 radians? It would be hard to determine that with my rubber band, but I happen to know that 360 degrees is about 6.28 radians. What's that number? 6.28 should be kind of familiar to you. If it's not familiar to you, then see if half of it is familiar to you. What's half of 6.28? .14, and that is 2 pi. So now we have our definition of what a radian actually is. 360 degrees is 2 pi radians. That just means our rubber band went around the circle about 6¼ times. If we wanted 1 radian, we could just divide both sides by 2 pi and have 360 degrees divided by 2 pi is 1 radian. Or we could reduce that fraction to 180 degrees over pi is 1 radian. Now, in the book, I believe on this page, you're given an illustration of an angle that subtends an arc length that is 2 radians long. You'd say beta has a measure of 2 radians. And then in the C part, you see an angle that subtends an arc that is in of length 3 radians. You say gamma is 3 radians. And then 360 degrees is 2 pi, which is about 6.28 radians. That's not actually what I was looking for. I was looking for this box. You can memorize that box if you want to. To change degrees to radians, multiply by pi over 180 degrees. To change radian to degrees, multiply by 180 degrees over pi. But if I just memorize something that doesn't make sense to me, I'm going to forget it before I leave the room. So I don't memorize what's in that box. I use unit canceling. Now, let me show you what I mean by that. If we know that 180 degrees is pi radians, we know that because 360 degrees is 2 pi radians, then we can change any angle that's given to us in degree measure by putting it over 1 and then multiplying by a fraction that has degrees in the denominator, because when I multiply fractions, I can cross cancel the common factors. I can also cross cancel the common units. I want a fraction that has degrees in the denominator and radians in the numerator, so that radians is what I'm left with. Now, a unit fraction is just a fraction that equals 1. And if we know 180 degrees is pi radians, then the fraction pi radians over 180 degrees is 1. And when we divide both numerator and denominator by 60 degrees, we find that 120 degrees is 2/3 pi radians. Oh, by the way, if you intend an angle measure to be degrees, you have to use the degree symbol to show that. But if you write an angle measure without a degree symbol, it's understood to be radians. So we don't have to write the word radians. We just say 120 degrees is 2/3 pi. And the same way with a negative 135 degrees, if I put it over 1, and multiply by a unit fraction that has degrees in the denominator, because that's what I want to cancel out, and radians in the numerator, because that's what I want to be left with, I can say pi radians over 180 degrees is a unit fraction because it equals 1, and then I can divide both numerator and denominator by 45 degrees. Negative 135 degrees is negative 3/4 pi radians. Now we could actually go back and do this B part of number 4 that we skipped. If we want two angles that are coterminal with 2/3 pi radians, what would we add to get a coterminal angle? We want to go all the way around the circle. If we're measuring in degrees, we add or subtract multiples of 360. If our angle is given to us in radians, we would add or subtract 2 pi radians. So an angle that's coterminal with 2/3 pi is 2/3 pi plus 2 pi. Or you can get a common denominator and say 2/3 plus 6/3 is 8/3 pi. To get another coterminal angle, you can take your 8/3 pi and add another 2 pi and get 14/3 pi is a coterminal angle. To get negative coterminal angles, subtract 2 pi. 2/3 minus 6/3 is negative 4/3 pi, and negative 4/3 pi minus another 2 pi is negative 10/3 pi. Now, this circle corresponds to a chart on page 327. This chart on page 327 gives you some common angles in degrees and their equivalents in radians. In calculus and pre-calculus, we're going to be using mostly multiples of 30 degrees and multiple of 45 degrees. And you're going to get to where you can convert those to radians really quickly in your head. Until then, like I said, when you get your unit circle and your Ziploc baggie in the mail, and I make that video, you'll see how 45 degrees is equivalent to pi over 4 radians, 90 degrees is equivalent to pi over 2 radians, and so on. So we'll fill this all out in a different video, but I just wanted to tell you, you don't have to memorize this chart on page 327. You're going to be able to run through it very quickly in your head in just a matter of days. All right. Number 16 in the notes say change the radian measure to a degree measure. And I know that these angles are in radians because no degree symbol is used. Just like I did with number 10, I can use unit canceling. I can write -5/2 pi as -5 pi over 2. That's the same thing. That's radians, so I need to multiply by a unit circle that has, it's not a unit circle, a unit fraction that has radians in the denominator and degrees in the numerator. Now I know that 180 degrees is pi radians, so this is the unit circle, unit fraction that I need. Now I can reduce it. The radians, this is radians, so both of the radians would cancel. And that's when the pi's would cancel. 2 goes into 180 90 times, and 90 times -5 is -450. So a -5/2 pi radian angle is equivalent to a -450 degree angle. And I just want to do one more of those. Pretty easy. Pi over 16 is in radians, so I'd need to multiply it by something that had radians in the denominator and degrees in the numerator, if that's what I wanted to be left with. Pi radians is 180 degrees, and 16 goes in, I thought it went evenly, but it does not. No, 16 doesn't go into 180 evenly. What about dividing both of them by 4? Four goes into 180 45 times. My pi's cancel. My radians cancel, even though I didn't have radians written on the angle I was given. And all I have left is 45 over 4 degrees. And that would probably look more normal if I wrote it as 11.25 degrees. So that's how we go back and forth between radian measure and degree measure. Number 18 says, write theta in terms of degrees and minutes and seconds to the nearest second. This is in radians. So I can put it over 1 and multiply it by the unit fraction 180 degrees over pi radians. And the radians would cancel. And I could punch on my calculator 3.1 times 180 and then divide that by pi. I'm going to use the pi button on my calculator. 3.1 times 180 is 558. Dividing by pi would give me, I'm just going to round this. I'm going to say 177.6169-ish degrees. But I want to change that to the nearest degrees, minutes, and seconds. Now, I'm going to show you the long way once, but then I'm going to show you how to do it on the calculator. 177.6169 degrees is 177 degrees and about 2/3 of another degree. Now we know that another degree would be 60 minutes. So if we multiply 60 minutes times that 0.6169, we would get that about 2/3 of another degree would be darn close to 37.014 minutes. And then if we want that to the nearest seconds, we could say 177 degrees plus 37 minutes plus some other tiny decimal part of a minute would be that times 60 seconds, because there's 60 seconds in a minute. Point 0.014 times 60 is about 0.84. So to the nearest whole second, that's almost another whole second. 177.6169, and I could have kept all the other decimals on my calculator, is equivalent to, or the nearest second, 177 degrees, 37 minutes, and to the nearest whole second, 1 second. Now, I don't want to do that every time I have to change decimal degrees to degrees, minutes, and seconds. So I'm going to show you how to convert this on my calculator. And then if you have a different calculator than me, you're just going to have to Google your calculator. And for example, I forgot how to change degrees, minutes, seconds, change decimal degrees to degrees, minutes, and seconds on this calculator. So I just Googled TI-30XA change decimal degrees to degrees, minutes, seconds, and it popped right up. It's this green function for me, this DD arrow DMS, is decimal degrees to degrees, minutes, seconds. And above the plus sign, it's degrees, minutes, seconds to decimal degrees. So if I started with this original 3.1 times 180 and divided by pi and got the 177.6169 and some other digits, that is decimal degrees. If I want to change it to degrees, minutes, seconds, I press second and then equals. Now, I rounded here, this 0.6169, and because I rounded, I came up to the nearest second. I came up with 1 second. If I had not rounded, if I had left all those other digits on my calculator, I would have come up with 177 seconds, 177 minutes. Let me try one more time. 177 degrees, 37 minutes, and 0 seconds instead of the 1 second that I did come up with. All right, so if you have a different calculator, you may have to Google just a few things to learn how to deal with some angle measurements on your calculator, but that won't be hard for you. All right, I'm going to do one more thing and then stop this video just so you don't have to watch a terribly long video. I'm going to show you how to convert from degrees, minutes, seconds to decimal degrees, or decimal degrees to degrees, minutes, seconds, which is what we just did on the calculator. Let me just again say this is how my calculator works, not necessarily how your calculator works. You may have buttons on your calculator that let you enter the symbols degrees, minutes, and seconds, but I don't have that. So to enter number 24, 320 degrees, 7 minutes, and 58 seconds on my calculator, I have to enter it in the form of degrees and then 2 digits for the minutes and 2 digits for the seconds. Now my degrees can be more than 2 digits because I could have, for example, a 590 degree angle, but enter however many digits you need for the degrees, but you have to enter 2 digits for the minutes and 2 digits for the seconds. Oh, I forgot one thing. On my calculator, I enter a period to tell my calculator where my degrees end and where my minutes and seconds begin. So here's what it looks like on my calculator. 320 degrees, and then point, my decimal. That's 7 minutes. I'll have to enter as 07 because I have to have 2 digits for my minutes, and then the 58 seconds has to be 2 digits also. That's degrees, minutes, and seconds on my calculator. If I want to change it to decimal degrees, then second and my DMS to DD key changes that to 320.1327778. If I want to round that to the nearest thousandths of a degree, here's my tenths, hundredths, thousandths. That's 3 decimal places. So to 3 decimal places, that would be 320.133 degrees. 7 minutes, or almost 8 minutes, is a very small fraction of a degree. This is a very small fraction of a degree. And then one more before we take a break. The next angle is given to us as decimal degrees, 81.7238. If I want to change that to degrees, minutes, and seconds, I would press second and then my equals button. And if I want to round that to the nearest whole second, that would be 81 degrees, 43 minutes, and would that round up to 25 seconds or 26 seconds? Well, this is actually 25.6 degrees, and 25.6 degrees would round up to 26 degrees. Man, it's hard to work the book and the document camera and my calculator and my tongue all at the same time. So forgive me for the stuttering that I'm doing. That would round to 81 degrees, 43 minutes, 26 seconds. All right, we're going to take a break and come back and do 5.1 part 2 on a different video in just a minute.